Okay. Yes, you're welcome. It's Loretta, right? Don't tell me I'm not learning. Okay. Did you have one in particular that you wanted to go over on the graphing ones? Okay. So going over the graphing in general, does anybody have a specific one of the graphing problems they want to see done with the calculator? Tommy? Sounds good to me. Is everybody else okay with that? All right. So 5 we asked to do by hand, but we'll do it on the calculator to just kind of check your by hand stuff. Sound good? So that'll kind of kill 2 birds with 1 stone there. So the first thing I'd want to do is I'd want to take a look at my equations that are in my system. And I'd want to rearrange those so that they're in slope-intercept form. So the first equation I don't have to do anything to because that's already in slope-intercept form. But the second equation I have to subtract the 3x from both sides and then divide by a -1. So that'll give me y equals 3x plus 6. And so now I'll just go to my calculator and graph those. So I pressed the y equals button and just typed in the 2 equations exactly as they appear. Probably the easiest way to look at the graph is to press zoom and then select Z standard. That was option 6. And as long as I can see the intersection on my screen, I am fine to proceed to the next step. If you don't see the intersection on your screen, then you'll have to fiddle with your window a little bit until you're able to find it. So let's just say hypothetically, like in the second quadrant, you can see the lines are getting close together, but they don't cross before the lines leave the second quadrant. What you need to do is you need to move further to the left and then further up, possibly, right? To see where they're going to actually cross. So to do that, if you go to your window, yes. Okay, come show me your calculator. So you see how this equal sign isn't highlighted? It's not going to graph. So you just need to move down and press enter on the equal sign, and that'll make sure that it graphs. You're welcome. So we're saying hypothetically we have the 2 lines that look like they're going to cross somewhere in the second quadrant, but not on our screen, right? They're getting close together, but they're not crossing in our screen. It looks like it's going to be somewhere to the left and somewhere up from our screen. So our left direction is our x min. We would just change that x min to be a smaller number like -20 or something. And then to go up, that's our x max. So we would change that number to be +20 or something bigger. And then hit graph and see if we can see the intersection. And if we can see the intersection, we're fine. If we can't still, then we do the same thing. Move a little bit further up and a little bit further to the left until we can see where they cross. Does that make sense, what I'm describing? So that's just changing your window manually. But we didn't have to do that because clearly we can see the intersection right on the screen, right? So now that I have my graph, I'm going to press second and the trace button. This is the same menu we used to do the maxes and mins. From this menu, we're going to choose the Intersect Command. And then the Intersect Command is going to ask us 3 questions. It's going to ask, what 2 lines do we want to find the intersection of? And then, where about do you want me to start looking for this intersection? So first curve, you notice that I now have a cursor on the screen, and it's already on one of the 2 lines. It's always going to start at the line in Y1. So if I press enter, you'll notice that my cursor now is automatically switched to line 2. So it'll all automatically switch to y2, which was the second line I wanted to find the intersection of. So I'll just press enter. And then it asks for a guess. The guess doesn't really matter. If you guess anywhere, it'll be fine. And then after you select your guess, at the bottom of the screen, it tells you the intersection. In this case, it's -1, 3. Loretta, are you happy there? Okay. Tommy, were you happy there? Okay. Mackenzie. Okay. So the solution is just the intersection, right? So it looks like that's at -1, 3. That's it. Homework 3. Yep, I'm just pulling up the sheet. So we're just solving this. The answer to this is quite gross. Did you get like a crazy fraction? Yes, that might be the correct answer. What is the fraction?
Well, I just put it in decimals and I did.
Ooh, don't do that. Why is putting it into a decimal a bad idea? Edmund?
It might not be the actual, can't be defined as a decimal.
Well, here's we're solving a linear system that we're doing right now. The answer, the decimal will always be able to be represented as a fraction. That decimal might be infinite though, or the decimal point might be so long that your calculator just can't even hold it, even if it does terminate somewhere. So the problem becomes when we go back and try to check that answer by plugging it back into the xy to see if it satisfies the equation. If you turned it into a decimal, it might not check exactly because of rounding, right? So Mackenzie, like, not that it's wrong necessarily to get a decimal, but you don't want to do that if you don't have to. So what was the result here? I was writing a key here this morning. It was like 181 over 19 and then -179 over 19 were the x's and y's.
Yeah, I got the -179, but
You didn't do the other one because you got such a weird answer. You're like, that can't be right. Give yourself some more credit than that. You did a good job. It was right. Do you still want to do it? I'm happy to do it. I just wanted to, before I started to do it, I wanted to let you know that, like, it's a weird answer. Okay. Yeah, that's fine. No big deal. So this side is the elimination ones, right? So before I get going on my elimination, the first thing I'm going to do is rearrange the equation so the x's, y's, and solutions all line up. So right now, for the first one, I'm going to add 4x to both sides and then subtract 9 from both sides. And then similarly, on the second equation, I'm going to subtract 9y from both sides. Okay with that. And we'll just refer to these again as equations A and B. So here, if I try to eliminate x or y, it's probably about the same amount of work either way. I think I'll do the y's though, because I only have to multiply by 9 and 5, which are pretty easy numbers to multiply with, as opposed to 11, which might get a little bit uglier. I don't really know. It's probably about the same. It's probably not much of a big deal. So I'm going to do 9 times equation A plus 5 times equation B. That'll give me the y's being 45 and -45 respectively. So if I do that, 9 times A is 36x plus 45y equals -81. And if I multiply 5 by equation B, that's -55x minus 45y equals negative 100. So that's going to give me negative 19x equals negative 181. So if I divide both sides by negative 19, I get x is equal to 181 over 19. Is that okay, Amy? And then to get my answer, I would just plug this back in to some place. It doesn't really matter where. I'd probably use this one because the x part is already by itself. I guess, I don't know. The numbers are smaller there. It's not really a good reason. It just looks like the better place to go. So if I do that, 4 times 181 is what? That's 400 plus 320 is 720, and then 4 more is 724, I think. And then we have to subtract 9 from both sides, but I need to make a common denominator there. 9 times 19 is 90 plus 81, so that's 171 over 19. So 5y equals... Okay, I'm done. It's calculator time. I'm too frustrated. I'm tired, guys. You know? Use that calculator. 553. Oh my goodness, look at what I did, guys. How come nobody's yelling at me here? Who sees the issue? What did I do? Yeah, is that supposed to be negative there? No, I don't know why I did it, but I did it. So this should be negative here. So negative 724 minus 171 is negative 895. That looks a heck of a lot better considering I know that this is not supposed to be some gigantic number in the numerator. I already knew it was. I said it was 171 already. Amy, are you okay?
Yeah, I was just wondering, so like, we don't need to get
Only if you're going to plan on graphing it.
Oh, okay.
If you're going to do elimination, it usually makes most sense to have x plus y equals constant.
That's what I was doing.
And to finish this up, we'll just multiply both sides by 1/5 to get rid of that. So there's y equals negative 171 over 19. If you guys are curious, the answer for number 8 is also pretty gross. What do I have? I have negative 59 over 57 and then 52 over 57. So a little less than negative 1 and a little less than positive 1. If you did decimals there, which you shouldn't do, looking for fractions for our answers. Amy, are you happy with that?
Yep.
Okay. I know the last name is Barr. What's the first name? Maya, thank you. Sure. So are you freaked out by the fraction? Well, let's make it so it has no fraction. Why not just multiply that first equation by 7? If I do that, I'll just have negative 5 minus 11x equals 7y. Does that feel more doable? Yeah, right? So does it matter if there's fractions for coefficients? Not really. We can just get rid of the fractions on the coefficient by like clearing the fraction out of there. Since we're going to potentially multiply the equations by something anyways, why not just take an extra multiplication step and get rid of the fraction so it's less of a pain to deal with. Doesn't that make life easier? You can do that really for any equation, right? If you have an equation, something with an equal sign in it, and it's got fractions in it, and you don't like having the fractions there, just multiply both sides of the equation by something that gets rid of all the fractions. You know what I mean? And then boom, there's no more fractions. I saw some of you guys do that on the absolute value solving stuff when there's some fractions in there. A couple of people did that here and there. It was like, oh, that's a clever way of getting around that. So if we were to finish this up now, Maya, we'll move everything, or move the variables onto one side and the constants on the other. So we'd have something like this. And I would probably use or eliminate the y's here because they're already opposite signs. I don't have to worry about multiplying through with a negative and possibly dropping some negative signs. But it doesn't really matter. That's not appreciably easier. So I'll just do 2 times a plus 7 times b. So when I do that, I get negative 15 equals 59, or 57x equals 59. And if I divide both sides by negative 57, I get negative 59 over 57. Is that okay there? And then to solve for y, I'll just plug this back into one of those locations. I would probably choose to plug it into here because the numbers are the smallest. You know, it just makes the arithmetic a little bit easier. So 5 times 59 is 295. And if I make a common denominator with the 7, 7 times 57 is 399. And 399 minus 295 is 184. 104, excuse me. Couldn't read my calculator there in the dark. And then if I multiply both sides by a half, which is the same as dividing by 2, that's my 52 out of 57. So we just had some yucky fractions on those last two, but that's okay, right? It's a little bit more tedious, but we can handle the fractions. We might have to go slow and be a little bit more careful, but we can deal with those things, right? It's not so bad. Alyssa, are you happy there? I'm sorry. Maya, are you happy there? I don't know why I called you Alyssa. Actually, I do know why. It's because I looked at the screen for a second and I saw Alyssa's name on it. You're good? Amy. It's a calculator question, right? Okay. So first thing I'm going to do is I'm going to rearrange this so that it's in slope-intercept form. So I'm going to subtract the 2x and then divide by negative 4. So negative 2x divided by negative 4 is 1/2 x. And then positive 10 divided by negative 4 is negative 5/2. And then similarly here, we're going to subtract 3x and then divide by negative 6. So negative 3x divided by negative 6 is positive 1/2 x. And then 10 divided by negative 6 is negative 5/3. And I don't even need to type this into my calculator at this point. I notice the slopes are the same, but the y-intercepts are different. So this has no solution. Are you happy with that? You're welcome. You could certainly type in your calculator, but there will be no intersection to be found. Doritos.
Is there an infinite solution if your equations are the exact same?
Yes.
Okay.
We happy with the homeworks? Okay. So today we're going to do two things. Get rid of that calculator. We're going to solve systems of linear inequalities. So an example of that could be something like something like this. So systems of linear inequalities are always going to be done by graphing because they're not equalities. There's no equal signs. You can't do substitution or elimination here. Everybody okay with that idea? So the first thing I'm going to do is rearrange these so I can get them into slope-intercept form. So the first one will subtract 3x and then divide by 4. And the second one will subtract 10 and then divide by -2. Notice that when we do that, because we're dividing by negative, the inequality symbol is going to switch directions. So far, so good? So I'm going to graph this equation with blue, and I'm going to graph this equation with green. So it really doesn't matter the x's or y's you pick, but I'm going to try to pick x's so that I get a whole number. So I notice that if x is 2, that's going to give me 6/4 here, which is the same thing as 1.5. That when I add it to a half, I'll get a good whole number. And then similarly, when x is what? Let's see here. 6, that'll give me 18/4, which is the same thing as 9/2. So when I add a half to that, I'll get a nice whole number. Again, there's nothing wrong with taking decimals there, but I figure if I don't have to deal with any decimals when I'm graphing, I guess I'd rather not. And it wasn't too difficult for me to do that. But there's no reason that you would not want to have a decimal there other than just not wanting to deal with a decimal, but they'd be okay to deal with. So there's nothing magic about the values I picked there. So here I don't have to worry about the same thing, right? I'll just pick 0 And that'll give me the y value of 5. And then maybe pick something a little bit farther away, like we'll pick 5. And then -2 times 5 is -10. So plus 5 is -5. So now we'll go ahead and graph. So let's do this. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 2, 2, and 6, 10. And just like when we graphed absolute value inequalities, since this is a strict greater than, I'm going to use a dashed line. And because it's greater than, I'm going to shade above. So here we have 0, 5. So 1, 2, 3, 4, 5. And then 5, -5. 1, 2, 3, 4, 5, -5. Here, because it's an or equal to inequality, we're going to use a solid line. And because it's less than, we'll shade below. So my solution set for this system of inequalities is the overlap in the shading. So it'd be like this region right there. And that's it. The picture is all we do. And when you're doing your homework or whatever, if you just want to draw or color in the overlap for the shading, that's fine. You don't have to color both regions. You could just color in where the overlap is. Does that feel okay? Should be pretty easy, right? You just graph a couple lines and then do some shading. The shading rules and the dotted and dashed rules are the same rules that we used for the absolute value inequality, so that shouldn't be too big of a deal to remember. Sound good? Yeah, I thought that would be okay. The second thing that I want to talk about today is solving 3-variable systems. I see. One minute while I look up my example that I wanted to use. Because I'd prefer not to come up with something that just has a bunch of crummy decimals in it for the first one, right? Or crummy fractions. Okay. So let's say we have the following system. So one thing I want to point out right away, just about my own penmanship, is my Z's are going to have a bar through the middle of them. My 2's will not. Now with my penmanship, I know that it's very difficult for me to tell the difference between a 2 and a Z if I don't do that. I'd recommend to you guys to do the same thing. I've seen many a good student get confused about what's a variable and what's a number on their own work, on their own sheet of paper, because the Z's and the 2's look so similar. You don't have to do that if you're confident in your penmanship. I would not be as a student, so just a little suggestion. Okay, so we'll do this problem both ways. We'll do it by substitution and elimination, then we'll make a decision about which one we think is the easier way to do it. Sound good? So let's do substitution first. I'll refer to these equations as A, B, and C, just so we have something to talk about. So what equation and which variable would be the easiest one to start with to isolate? Paul. Okay, so we're not doing elimination right now. We're doing substitution first. Okay, so the variable that I would want to isolate is either the Z in equation A or the Z in equation B. The reason being, if I try to isolate any other variable, I'm going to end up with some fraction somewhere in my equation, and I'd prefer not to have that happen. It's not a problem if it happens, but it slows everything down and just makes it a little bit more complicated. It's not wrong if you choose to do something like that, but if I can avoid having to deal with fractions for as long as I possibly can, that would be my preference personally. Is everybody okay with that idea? So just for the sake of argument, let's use equation A. So to get the Z by itself, we'll subtract 4x, subtract 4y, and there's my new equation. Everybody okay with that? So I'm going to substitute that now into equation B. Oh, let's do it that way. So let's say A into B. So we have 2x minus 4y plus, and then instead of Z, I'm going to write minus 4x minus 4y plus 24 is equal to 0. And similarly, I'm going to take A and plug it into C. So I'll have 5x minus 4y minus 5 times my value for Z, which is minus 4x minus 4y plus 24, and in this case equal to 12. Everybody so far so good? Okay, so now in this first equation, I'm just going to combine like terms. Since there's no coefficient in front of the Z, I can just do that directly. So it'll give me minus 2x minus 8y plus 24 is equal to 0. And then I'll just move that 24 over to the other side. And then for my second equation, where I've plugged A into C, I have to distribute this negative 5. So negative 5 times negative 4 is positive 20. And negative 5 times positive 24 is negative 120. And if we combine these, 25 or 20x and 5x is 25x. Negative 4y and positive 20y is positive 16y. And then if I add the 120 over to the other side, I got that. So this I'm going to refer to as equation D, and this one as equation E, and that's going to form a new system. Notice, though, that this new system has only 2 variables instead of 3 variables. So I'll pause here. I see a lot of people still writing, so I'll just pause here and let everybody catch up. While you're writing, start thinking about which variable in which equation we want to isolate next. Because here I think there is an obvious choice. How many of you were thinking I would want to do the variable x in equation D? The reason being, when we divide by 2, we don't have any fractions, right? Not that making another decision would be wrong, but if we can avoid having to deal with fractions, let's do that, right? It just takes a moment to look at things, and if we have that capability, that would be great. So to isolate the x, I'm going to add the 8y to both sides and then divide by negative 2. So that's going to be negative 4y plus 12. And then I'm going to plug equation D into equation E. So that's 25, and instead of x, we'll have minus 4y plus 12 plus 16y is equal to 132. Notice now there's only one variable left. So we'll distribute that 25 so we can start solving for y. So we have negative 100y plus 100 and, oops, sorry, that's not right. 250 plus 100, so that should be 250 plus 50 should be 300. Yeah. Plus 16y equals 132. So we combine like terms, negative 84y plus 300 equals 132. If I subtract 300 from both sides, I get 168, negative 168, excuse me. And if I divide both sides by 84, I get y is equal to 2. Now, I'm going to solve for x by taking the answer and substituting it back into this equation. So that tells me x is equal to 4. So now I have x and y. What I'll do next, both of those and plug it back into this equation to get my z. So that's going to be negative 16 minus 8 plus 24, which is equal to 0. So my answer then is always in alphabetical order, x, y, z. And again, I'll pause here for a minute for anybody that's still writing in case they need to kind of catch up. Does the color coding help when I do that? As I change from one step to the next or whatever? I'm trying to make it easy to follow if you're looking back at it anyways. So let's solve this same system now, but this time we'll use elimination. So the idea here with elimination is kind of the same as the substitution. So again, what I'm going to do is I'm going to pick a variable to eliminate. And my goal is to eliminate the same variable from two pairs of these equations. So the first thing I'd want to do is I'd want to pick a variable to eliminate. And there's an obvious choice here looking at it that appears to be very easy. Which variable seems like the best choice? The y's, right? I notice that I have positive 4y, negative 4y, and negative 4y. So for example, if I add a and b, that will eliminate the y's. And if I add equations a and c, that'll also eliminate the y's. Is everybody okay there? Yes. Sure. Yeah, no problem. I was still way zoomed out from when I was going backwards on the other one. Okay. Is everybody okay with that reasoning? Now, it's super important when you do this first set of eliminations that you're eliminating the same variable with each pair of equations. You can't eliminate the x's in one pair and the y's in another pair, because when you try to do the next elimination, you won't be able to eliminate the same, you won't be left with one variable again. You'll still have two variables and then what to do. So I'm not going to rewrite the equations a and b since we didn't alter them at all. I'm just going to read them off from above. Is that okay with everybody? Okay. So 4x and 2x is 6x. 4y and negative 4y is nothing. Z and z is 2z. And 24 plus 0 is 24. And then a plus c, 4x plus 5x is 9x. 4y plus negative 4y is 0. Z plus negative 5z is negative 4z. And then 24 plus 12 is 36. I'm going to refer to these as equations D and E. And these are going to come together to make a new two-variable system. Are we okay there? Already, which one seems easier to deal with? This seems like so much less writing, doesn't it? The elimination. This is kind of the big advantage of elimination. As you go deeper, everything gets shorter. Like the equations all get smaller and there's no simplifying to do in between. The substitution, everything gets longer and then folds in on itself to get shorter again, but it has to get really long before it gets short again, which I think is a big advantage to the elimination. It's just so much less to write. Okay, let's pick a variable to eliminate now. Which one looks easier, x or z? Z, good. How would you do it? 2d plus e, right? Here, since I've changed one of them, I'll write it out. So 2 times 6x is 12x. 2 times 2z is 4z. And 2 times 24 is 48. I have 9x minus 4z is equal to 36. So 21x is equal to 48 and 36 is 84? Yeah, 84. And if I divide both sides by 21, then I get x is equal to 4. Everybody okay there? Now to solve for my next variable, I'm going to go back to one of my two-variable systems. I'm going to choose to use the first one. So I'll plug in 4 for x, and then solve for z. Subtract 24 from both sides, divide both sides by 0 or by 2, and I'm left with z equals 0. Are we okay there? Okay. And then my last step, I'm going to take both of these two answers and plug them back somewhere into equation A, B, or C, one of the 3 variable equations. I'm going to choose to plug them into A. So I have 4 times x. Maybe we'll write that in dx in red. Plus 4y plus z, I'll write that one in green since I used the green arrow there, is equal to 24. So 16 plus 4y plus 0 is equal to 24. If I subtract 16 from both sides, I get 4y is equal to 8. If I divide both sides by 4, I get y is equal to 2. So if I put it together, I have 4, 2, 0. Is everybody okay there? Personally, I think the elimination is a lot easier to keep track of things. There's much fewer symbols rolling around. The equations are much shorter in general. Paul, what's up? Right. Yep. No. Again, like what variable you choose to eliminate first does not matter, right? If you choose to do the x's first or the z's first or whatever, that's fine, no big deal. Eventually we'll end up with the same answer regardless of what variable you choose to eliminate in what order. A by 3 and B by 2. No, because you'd have 2z plus 3z would be 5z.
Oh.
Okay. Okay. Let's stop here because I'd like to give you guys a little bit of time anyways in class to start on things. So for Sunday's homework check, I'm going to ask you guys to do, oh, I don't have them in there yet. Let me pull them from the other classes. Homework 2 and homework 5. So in homework 2, we're just asking you to graph some system or solve the system of linear inequalities. The solution set is just the graph. And what do I have? I have 4 of those to do. That's no big deal, right? And then in homework 5, we have 5 3-variable systems to solve. Please don't try to do all your work in the little tiny space I provided. Like, take the problem and take like a whole column or something to do it and then do the next problem if you're going to do it in OneNote. The reason I say this is just that in my experience, neatness for students really makes a big difference in keeping track of what's going on, because there's a lot of symbols in any one of these 3-variable problems to keep track of. Try to be neat, try to be organized. It makes a huge difference. Give yourself lots of space to do the problem. Don't try to like squeeze it all in some little tiny place. At least until you're like a pro expert at doing this. Okay? And we'll do some more 3-variable practice next time and deal with some of these unusual cases. Then, okay? Sound good? Okie dokie.